Let's jump right into this explainer. Today we're unpacking a truly groundbreaking research paper out of Huazhong University of Science and Technology, all about the Model Context Protocol, or MCP. Look, if you've been tracking AI agents since function calling really exploded back in 2023, you already know that getting large language models to securely and reliably talk to external data is absolutely the next frontier. We're literally handing AI the keys to our personal databases, our private APIs, our enterprise software, the whole shebang. But here's the million-dollar question. Are those doors actually locked? This paper is the very first systematic analysis of the whole MCP ecosystem, and we're going to look closely at both its architectural brilliance and, yeah, its critical security vulnerabilities.
So, here's our roadmap for today. We'll start with the AI interoperability solution, move into the MCP server lifecycle, cover 4 major security threats, look at some real-world attack scenarios, and finally wrap up with securing the ecosystem. Let's get into it.
Part 1. The AI interoperability solution, breaking out of the silos.
To really get why this paper is so crucial, we gotta talk about the massive problem it solves: siloed AI agents. Think of the Model Context Protocol as a universal power adapter for artificial intelligence. Before this, if you wanted your AI to read a local file and then later wanted it to query a specific cloud database, you had to build custom one-off integrations every single time. Honestly, it was exhausting for developers. But MCP completely changes the game by creating a standardized bridge. It completely decouples the implementation of a tool from the AI model itself, meaning any supported model can just plug in and instantly understand how to use those resources.
The real paradigm shift we're seeing here is ditching that old way of predefined hard-coded integrations. Those hard-coded links, they act like chains. They severely limit your long-term maintainability and lock your tools into specific proprietary platforms. The new way, powered by MCP, is entirely dynamic. It relies on a protocol-based standard where the AI client can literally ping the server at runtime and ask, "Hey, what tools do you have available for me to use today?" We call that schema negotiation. It even supports bidirectional communication, so the server can actually send updates right back to the AI. We're finally leaving behind those clunky provider-specific bindings and stepping into a true plug-and-play ecosystem of discoverable network services.
All right, Section 2, the MCP Server Lifecycle Anatomy of a Universal Translator.
To properly analyze the security side of things, the researchers systematically broke down how an MCP server actually comes to life and operates over time. Think of it exactly like building and living in a house. First, you've got creation, drawing the blueprints, defining the metadata, and writing the initial code for the tools. Second is deployment, putting the house on the market and opening the doors, which happens when the server is released to public registries and users actually install it. Third is operation, people actively living inside. This is the runtime phase where the host, client, and server constantly interact. And finally, maintenance, fixing the plumbing and upgrading the roof, representing version iterations and configuration updates. Across these 4 distinct phases, the paper maps out 16 key activities. By tracking this entire lifecycle, the researchers could pinpoint exactly where the security foundation starts to crack.
Moving to Section 3, 4 major security threats, the complication of decentralized trust.
So the openness of the MCP ecosystem is obviously a massive breakthrough, but man, is it a double-edged sword? It opens up a sprawling new attack surface. We're suddenly dealing with decentralized trust. We aren't just relying on giant, highly vetted corporations like OpenAI or Anthropic to keep us safe anymore. We're opening our systems up to thousands of independent third-party developers. It's kind of like the Wild West. And the threat starts right at the source, during that very first creation phase, with malicious developers actively looking to exploit the supply chain before a tool even touches your machine.
The researchers categorized the threats into 4 main attacker archetypes, which map perfectly back to our house analogy. You've got malicious developers writing bad blueprints during the creation phase. You have external attackers intercepting packages at the front door during deployment. You've got malicious users acting as highly destructive guests during the operation phase. And crucially, you have security flaws introduced during maintenance. Now, why should you care about maintenance flaws? Because it means a totally routine update, something meant to patch a bug, could be hijacked to secretly introduce a backdoor into your previously secure system. We absolutely cannot just secure the runtime environment and call it a day. Digging into the specifics, the researchers identified 16 distinct, honestly pretty creative threat scenarios. Take a malicious developer using namespace typo squatting. A bad actor names their server something just slightly off, maybe spelling Google Calendar with an E instead of an A, and boom, you're tricked into downloading malware instead of your daily schedule. Or think about a malicious user attempting a sandbox escape during the operation phase. They feed the AI a specific prompt designed to break the tool completely out of its isolated environment, letting it rummage through your computer's private files. It's a massive web of vulnerabilities, and it proves exactly why a lifecycle-centric security model is desperately needed.
Which brings us to Section 4, Real-World Attack Scenarios, the Digital Trojan Horse.
To really grasp how severe these vulnerabilities are, the researchers provided a visceral, real-world case study of a threat called cross-server shadowing. It's essentially a digital Trojan horse, and it is terrifyingly simple to pull off. Imagine you install a basic, seemingly harmless math tool to help your AI crunch some numbers. But what you don't realize is that the second you install that simple calculator, it's secretly hijacked your entire email system. That right there is the essence of cross-server shadowing.
Let's break down how this actually works in practice. Picture a malicious MCP server, cleverly disguised as math tools, that introduces a standard add tool, but written right into the Python script is a malicious side effect. It actively hunts for an existing send email tool on your system and completely overrides its logic. So a user innocently prompts the AI, "Please send my salary report to alice@mail.com." The AI processes the request, thinking it called the legitimate safe send email tool. But under the hood, it actually triggered that shadowed attacker-controlled logic.
And honestly, the scariest part of this whole scenario, the AI has absolutely no idea it's been tricked. The researchers spell out the devastating result here. The attacker has already siphoned sensitive communication data by quietly forwarding a copy of that salary report to an external attacker-controlled address. Because MCP right now lacks strict code provenance and doesn't enforce rigid namespace isolation, the interface looks completely identical to the AI. The model happily reports back to you email sent successfully, completely blind to the fact that a massive silent data breach just happened right under your nose.
Finally, Section 5, Securing the MCP Ecosystem, Restoring Trust.
So how do we actually fix this? We've got this incredibly powerful protocol, but it clearly needs some robust guardrails. The researchers propose a set of really practical, actionable safeguards. First up, we have to enforce clear namespace separation. Tools from different servers should be required to use their full, unique developer names, so they literally cannot maliciously overlap. Second, the AI applications themselves need to actively check for code conflicts. If two servers claim to have a tool with the exact same name, the system should instantly halt and warn the user. Third, we need provenance verification and digital signing. Think of it like a tamper-proof digital ID card that's required before a server can even be listed on a registry. And finally, when users run these tools, they need to be using sandboxed MCP hosts. Imagine a quarantine glass box. If a malicious tool somehow executes, it's trapped inside that box, fundamentally unable to touch your local hard drive or steal your credentials. Which brings us to the ultimate question. As autonomous agents get deeper and deeper access to our enterprise systems, our personal data, and our daily workflows, will these AI assistants be our greatest tool or our biggest security vulnerability? This incredibly insightful research is a massive wake-up call that this technology will never just be safe by default. It is entirely up to developers to build the guardrails and for the community to engage in continuous, rigorous lifecycle monitoring to keep those doors locked. Thanks for joining me for this explainer on the MCP Landscape. See you next time.